Hi, everybody. So as I mentioned in the discussion of public key cryptography, to make that algorithm and others that use modular exponentiation practical, we need an efficient way to raise numbers to powers mod n. And so I'm going to take a little bit of time to describe an algorithm known as repeated squaring, which is described in the text at an earlier point in the book. We skipped it. Now we can kind of come back to it. So let's look at the following problem. We want to compute 2 to the 43rd mod 101. And what's the best way to do that? Well, one thing we could do is we could take 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, and so on. And if we did that 43 times, we would eventually know what 2 to the 43rd mod 101 is. And one thing we would be able to do along the way is if we kept reducing numbers mod 101, at least we would never have to worry about our numbers growing. They would always keep getting reduced mod 101, and so they would stay relatively small. But we would still have to do it 43 times. And if you imagine that n was, let's say, a 100-digit number, and d was a 100-digit number, then raising something to a 100-digit number by this method would require you to do 2 times 2 times 2 times 2 times 2 times 2 as many times as are in a 100-digit number. And there's no computer that we have. I mean, this would take many times the age of the universe to get through. So we need another approach. And the trick here is to look at the number. Here we want to compute 43, to write 43 in base 2. So what is 43 in base 2? Well, it's 32 plus 11, which is 32 plus 8 plus 3, which is 32 plus 8 plus 2 plus 1. In other words, it's 2 to the 5th plus 2 cubed plus 2 to the 1 plus 2 to the 0. Now, why does this help? Well, think about what happens if we want to raise, let's not use 2 for the moment, let's just look at a to the 43. So a to the 43 is a to the 2 to the 0 plus 2 to the 1 plus 2 to the 3 plus 2 to the 5th. And that's equal to a to the 2 to the 0 times a to the 2 to the 1 times a to the 2 to the 3 times a to the 2 to the 5th. But how do you compute a to the 2 to the n? Well, you take a and you square it, and you square it again, and you square it again, and you do that n times. In other words, it only takes n multiplications, not 2 to the n multiplications, to compute a to the 2 to the n. So if we wanted to compute a to the 43rd, we can start with a to the 2 to the 0, that's a, and then we multiply that times a squared. So let's work it out. What is 2 squared? That's 4. So a is 2, so we would have 2 times 2 squared, which is 4. And now we need to know what is 2 cubed, but that's 2 squared times 2, that's 8. And finally, we need to know 2 to the 2 to the 5th. And to get that, we take 2 squared and we square it, that's 16. And then we multiply that times 2 and we get 32. So working out a to the 43rd, we had to compute 2 squared, 2 cubed, 2 to the 4th, and 2 to the 8th, and 2 to the 16th, and 2 to the 32nd, just by squaring 2 over and over again. And then we had to do the multiplication of this times this times this times this. So how many multiplications was that? 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications. That's a lot fewer than 43. Now, this is kind of ungainly here, and I'm going to sort of skip some steps and show you how to do this in a kind of an automatic way, where you don't have to first work out what the binary expansion is of your exponent. You can just follow these instructions, or if you know a little bit of programming, it's easy to write a computer program to do this. So here's the algorithm. It's called repeated squaring, and our goal is to compute a to the e modulo n So we're given a, which is the base, e, which is the exponent, and n, which is the modulus. And here's what you do. You make a little table. You label the headers S for squares, P, I don't know what that stands for, and T, I don't know what that stands for. And the first row of the table has the base in the first column, 1 in the second column, and the exponent in the third column. And now you do the following steps. You first look to see if this number is even or odd. If it's odd, you multiply the S times the P column and you write it in the P column one step down. If it's even, you just copy the P step down. So that, in this case, it's odd. So we did 2 times 1 and got 2. And then you square the S column. So now your next row is 4, 2, and 21. Now you repeat this. 21 is odd, so you multiply 4 times 2 to get 8. You divide 22 by 2, dropping any remainders to get 10, and you square 4 to get 16. 10 is even, so you just copy 8 down to the next row. You square 16, so 16 squared is 256, but we're working mod 101, so if you take 202 and subtract, you get 54. So this is actually 16 squared mod 101. So you do all your calculations mod n, and you divide the 10 by 5. Now this is odd. It's 5. So you multiply 54 times 8 mod 101, and that turns out to be 28. You square 54, and you get 88 mod 101. And you divide the 5 by 2, dropping any remainders, and it becomes 2. Now this is even, so you just copy P down. You square the 88 to get 68. You divide the 2 by 1, and you get 1. And now you've reached the point where T is 1, so you go to the final step, and the answer is the S number times the P number, or 68 times 28, which mod 101 is 86. So the result, 2 to the 43rd, is actually congruent to 86 mod 101. Now, how long does this algorithm take in general? Well, the number of rows in this table is the number of times you can divide your exponent by 2 until you get to 1. And then, so it's, another way to think about it is it's the largest power of 2 that's in the exponent. And yet another way to think about it is this takes log base 2 of n steps, more or less. So instead of taking n steps where you have to do 2 times 2 times 2 times 2 times 2 times 2, or sorry, e, log base 2 of e steps, it takes the log base 2 of that. So that means that if you were raising something to on the order of 1,000, instead of taking 1,000 steps, it would take 10. If you were raising something to the order of 1,000,000, instead of taking 1,000,000 steps, it would take 20 steps. So the number of steps grows like the number of digits in the number, not like the size of the number. And that completely changes things. So my earlier example of a 600-digit number, that just is going to take 100 times longer than a 6-digit number, not 10 to the 600 times longer. So why does this algorithm work? Well, let me walk through a proof, and this may take a little bit of thought and see where we are. So we're going to prove that this algorithm works by induction. And the first observation that I want to make is that suppose you run the algorithm starting it out with S, the first column having A, 1, and E, and you get some answer. If instead of putting A, 1, and E in the first row, I had put something else instead of 1 here, let's say I'd put some number K in for this position, that K gets multiplied and comes down here at each step. And the final answer, the last row here would have a K in it, and the final answer would be multiplied by K. So one way to think about this is that the algorithm, if you run it with P equals 1 and you get some answer, if you change the initial conditions and you put a K in the first slot for P instead of a 1, you would multiply your final answer by k. And we're going to use this. It's a little lemma. Now, the first step in our induction is the case where e is 1. And if e is 1, the very first thing that happens is that we return s times p. And remember that at the beginning, s is a and p is 1. So we return a, which is in fact a to the 1. So the first step of the induction checks out. And if you run the algorithm with e equals 1, it returns s times p, which is a to the 1. Okay, so now suppose we're going to use strong induction. Suppose the algorithm works for all exponents up to the exponent we're interested in, and we want to show it works for that exponent. Well, there are two possibilities. Our exponent could be even. So remember the way the algorithm starts is it has s, p, and t, and it has a, 1, and e. If the exponent is even, then the very first step is it replaces s by a squared, it carries the p down without changing it, and it replaces e by e over 2. And since e is even, it really is e over 2. The rest of the steps are the same as if we had run the algorithm with an input of a squared and an exponent of e over 2. And by our inductive hypothesis, from here on, we compute a squared to the e over 2 mod n, which is actually equal to a to the e mod n. So if the exponent is even, the first step just reduces us to the case where we've divided the exponent by 2, which is smaller than e, and therefore when the algorithm runs, it will end up computing the answer that we want. What about if e is odd? Well, if e is odd, we again start with a, 1, and e, and the next step is going to be a squared, a, because since e is odd, this is s, p, and t, we multiply s times p and we get a. And then we replace e by e over 2, dropping remainders. But exactly that means we take e minus 1 and we divide it by 2. So e is odd, we subtract 1 and now it's even, and then we divide it by 2. And now we have an exponent which is smaller than e, but we've got our p column has an a in it instead of a 1. And here we use our little observation from before, our little lemma, and we know that this is going to compute a times what we would have had if we'd put 1 here, which would be a squared to the e minus 1 over 2 mod n. And that works out to be a times a to the e minus 1 mod n, which is congruent to a to the e mod n. So again, by induction, we see that if we know that the algorithm works for all exponents smaller than our exponent, then it's going to work for the exponent that we're interested in. And so this algorithm computes modular powers, and it does it with a number of steps. The running time, or the number of steps, is like the logarithm base 2 of the exponent. And since the exponent is always going to be less than n, this is going to be at most the log base 2 of n. And that makes it practical even if n has hundreds of digits.